Previously in this series, we've explored how the Schmidt lab team is working in the lab to assess soil health properties. We've talked about soil respiration, we've talked about soil bugs, and today we're going to talk about soil aggregation, specifically water-stable soil aggregates. So why do we care about these? Soil aggregates are clumps of soil. If you dig a hole and the soil comes out as dust, as individual particles, then there were no aggregates. But if there are clumps, those are aggregates. And those are important for a couple of reasons. Aggregation means that soil is sort of sticking to itself. And that means that it's less likely to move, it's less likely to blow away in the wind, or it's less likely to erode with water. And you may be wondering how aggregates stick together. Well, they stick together through carbon. There's some differences depending on the type of soil that you have. So clay and sand have different charges and different shapes, and so they'll react differently when you add organic carbon. But generally speaking, increasing organic carbon increases the size and stability of your aggregates, and increasing the size and stability of your aggregates reduces how much erosion you're going to have. Also, aggregates provide little homes for bacteria. But also, the other important thing is that aggregates are not just little bits of dirt all stuck together. They're little bits of dirt all stuck together with space between, because little bits of dirt are not totally square. So when you get down to the microscopic level, when they're all stuck together, there is little pore spaces in there, and those spaces allow for water and for air to stay in the soil, which makes them accessible to plants and animals and bacteria that are living in the soil, which is why soil aggregates are one of the best indicators of healthy soil, because they are essential to provide the resources that soil organisms will need. So, one of the things that we can do to measure how healthy a soil is to measure how stable the aggregates are. And when we talk about stability, we mean stability to water. If you've seen a mudslide, then you know that when there's enough water in dirt, it will move. So that's when soil is most vulnerable. Soil aggregates are most vulnerable is when they're wet. So what we're going to do is to test how stable the aggregates are. And we're going to do this by soaking our soil samples and then shaking that wet soil. Today we're going to watch Seth. And so what he's going to do, it's going to take some of our soil samples that we've collected, and he's going to put them on the very top of a set of sieves. And that means that as soil falls through the sieves, the progressively smaller and smaller openings, and so wherever those pieces get stuck, wasn't able to fit through, so it must be at least slightly bigger than the holes. So he's going to put this stack of sieves inside a water tank, and on top of that, we'll put our soil samples, and then we'll start the shaking and the sieving. We're going to let it soak. Then we'll start sieving and shaking process. So for 10 minutes, we're just gonna let them shake, and the particles will start falling through the sieves. And then we're gonna take out all of the soil that's on the different sieves, and then we're going to dry it and weigh how much was left in the first sieve, and the second sieve, and the third sieve, so on and so forth, all the way down to the bottom. And then we'll calculate what is the mean weighted diameter. And the bigger the mean weight diameter is, that means that there was a higher average particle size that was stable in water, stronger aggregates, and the mean weight diameter is bigger. And we'll be able to use that information to tell us whether the treatments that we originally applied to the different soil samples are helpful to improving soil, reducing erosion, improving drought resilience, all from this one little shaker. Well, that's what we have going on today in the Schmidt Lab. Thanks for watching.